Okay, page 137, number 1. Find the weight of a 2.3 kilogram bowling ball on Earth. So it's telling you the mass is 2.3 kilograms, and it's asking you for the weight, Fg. So our equation is just Fg is equal to mg, 2.3 kilograms. It just says on the Earth, so we assume g is 9.81 meters per second squared. Type this into your calculator, and you should get 22.563 newtons. And that would be down. Number 2. You weigh 652.58 newtons down. So this time they're giving you the Fg, 652.58 newtons. Going down, and it says, while standing on a spring scale on Earth near the equator. So you got to go to your chart on page 132, and look up little g of the equator. And when you do, you'll find that it's 9.7805 meters per second squared down, and it wants the mass. So Fg is equal to mg, so your m is just equal to Fg divided by g. So your 652.58 newtons divided by your 9.7805 meters per second squared, and you should get a mass of 66.72256 kilograms. This is part A. Part B says determine your weight on Earth near the North Pole. So remember, your weight changes depending on where you are, but your mass doesn't. So now you're looking for Fg, and you have your mass from part A. So your mass is 66.72256 kilograms. You go back to that chart on page 132, and you look up little g for the North Pole, and it's 9.8322 meters per second squared. And when you do this, you get an Fg of 656.0295556 newtons. Okay, so a bit more than what you were at the equator, and that's because, remember, the Earth is bulging at the equator and flattened at the poles, so the poles are actually closer to the center of the Earth, which is why little g is bigger. C wants to know what's your weight on the International Space Station. So again, you're going to do Fg equals mg. You're going to still use your mass from part A, 66.72256 kilograms. And you're going to go back to that chart one more time and find the little g for the International Space Station. It's 9.0795 meters per second squared. And so when you do this, you get an Fg of 605.8075 newtons. And that one's down, and so is this one. Sorry, I didn't write it in. Okay? So again, significantly less than the other ones. Second part of this question says, why would this value be impossible to verify experimentally? The answer is what we talked about the other day, because everybody's floating around in the International Space Station in free fall, and so they wouldn't be able to stand on a scale to find out their weight. The lunar roving vehicle, pictured here, this is number 3, has a mass of 209 kilograms, regardless of where it is, because remember, mass doesn't change. But its weight is much less on the surface of the moon than on the Earth. Calculate the weight on Earth and on the moon. So the weight on Earth, Fg is equal to mg. So Fg is equal to 209 kilograms times, doesn't say where on Earth, so we assume 9.81 meters per second squared. And so we get an Fg of 2050.29 newtons. So that's for the Earth. Now for the moon, you need to go to the chart on page 133 and find the little g for the moon. Okay, so it'll be the 209 kilograms. And when you look up little g from the moon on that chart, it's 1.64 meters per second squared. and you find out that this thing has a weight on the moon of 342.76 newtons, significantly less than on the Earth. Okay? And number 4 says a 1 kilogram mass, so m is equal to 1 kilogram, is used to determine the acceleration due to gravity of a distant city-size asteroid. Calculate the acceleration due to gravity, so we're looking for g. If the mass has a weight of 3.25 times 10, so Fg is 3.25 times 10 to the negative 2 newtons down. So again, Fg is equal to mg. You're looking for a little g this time, so divide both sides by m. So Fg divided by m, so 3.25 times 10 to the negative 2 newtons divided by 1 kilogram. Hopefully you don't have to type that in your calculator. 3.25 times 10 to the negative 2, a newton divided by a kilogram, meter per second squared, down. Okay, so there are the 4 questions from page 137.